All right, lesson one, part three. I'm glad you made this far. I'm gonna hopefully get done this segment. If not, well, and I hope you're not watching these at regular speed. I hope you're speeding them up and like clicking through and stuff. Anyway, okay. So when we just talk about independent events, but when it does have an effect, there's a type of event called dependent, where one affects the outcome of the first event affects what's going to be the probabilities of the second event, and that totally happens. And marbles in a bag, when you don't replace them, is really like without replacement is what we call this. That's really a very popular thing that happens in real life. Then this is modeled by not replacing the marbles or blocks. Okay, so let's draw a tree diagram. So in the first part we have blue and green, and the second one we also have blue and green. I will fill some stuff out. So in the beginning we just have 3 of the 5 are blue and 2 of the 5 are green. But then after that, we don't replace it. So there's only 4 left in all of these situations. There's only 4 left in the bag for the second draw. So already there's some different probabilities. None of these probabilities are going to be the same as what they were before. And after we take a blue one out, so now this is after we've gone down this path, the blue one's gone. We've got a new bag now, essentially, that has 1 less blue in it. It has 2 blue, and it still has 2 green. So these are the probabilities here. And here, after we pull out a green, this still has 3 blue, but now it only has 1 green, and these are all different. Let me finish the end of the rows. All right, so there's the rest of those probabilities, and they do come out a little bit wonky. And now there's 20 possibilities, which is a little weird, because there's 5 possibilities in the first bag, and there's 4 possibilities in the second bag. All right, but again, once we're armed with the results of the whole sample space here, life is easy when it comes to actually answering the questions. So if you haven't figured this out yet, the setup is kind of a lot of work, but oh my gosh, then ask me anything and I'm ready. All right, probability no blocks are green, I guess, if you read carefully. That would just be the 6 out of 20. Both are green is just 2 out of 20. That's kind of a low probability. Sorry, 2 out of 20. And 1 is green and 1 is blue. That would be all of these, which is all 12 in the middle. Okay. All right, so if they're independent, I've said this before, if they're independent, you can go ahead and multiply. If they're dependent, and all these are probabilities, right? So these are fractions. This is a fraction. The whole thing turns out to be a fraction. It's not like number of outcomes and number of outcomes. It's fraction times fraction equals fraction. If they are dependent, we have to adjust for that in the second multiplier. So that's kind of what is, okay, so this is called condition probability. It's called the probability of B given A. So that little slash thing there means given that. So that's what's going on here. So this is the probability the first one was blue. This is the probability, technically, to read this. This is the probability the second one is blue, given that the first one is blue. This is the probability the second one is green, given that the first one is blue, etc. And that's written this way. Okay. Okay, back to the deck of cards. I made this a little, sorry, this is a little small, but I had to fit this on one page, kind of, and this is what I decided to do. All right, what's the likelihood that the first card, oh, so what are we doing here? 2 cards are drawn without replacement. All right, so this is going to be, there's 52 choices for the first one without replacement. Then that's going to be slightly different, right? So it's like the bag with the blocks in it on the last one. The second bag is only going to have 51, or the second draw really now is going to come from 51 cards. And those 51 cards are affected by what's pulled out first, right? If we pull out an ace first, then we got a card with, or we have a deck of cards now with only 3 aces in it. So this is what this is going to feel like. And this is a very common thing to have to do in these kind of problems. All right. What's the likelihood the first card drawn is a king? Oh, that's just 1 card, so that's fine. That's just out of 52. I don't have to think about the second card. That's just 4 of them. There are 4 kings. If the first card is a king, what's the probability that the second card will be a king? Okay, so now we're talking about the second card. The second card, there's only a deck of 51 to choose from. And here what they're asking us for is really the probability of king given king, like probability that the second card is a king, given that the first one was already a king, if you want to follow the notation. So given that the first one's a king, now there's only 51 choices left. What's probably the second card's also a king? That's 3. They're not asking the probability of drawing 2 kings. That's a different question. They're saying, let's say you've taken a king out of the deck. Now what's the probability that the second card is a king? So that this first card being a king is a known thing that's already happened. Again, that's different than saying, what's the probability of drawing 2 kings? I would have to multiply this first by 4 out of 50. I'd multiply these together, which is what D is. So I might as well say this here. D is what, and they just changed to queens for some reason. The first one's a queen, and then after that, the second, that's a 3. The second one's a queen. I'll do that in the calculator. If the first card's not a king, what's the probability the second card will be a king? Again, we know that the first one was not a king. We pull out a non-king from the deck. There are 4 now of the 51 remaining cards that are kings. I will do this in the calculator in a second. What's the probability that both cards are diamonds? What's the probability that the first one's a diamond? Well, that's, all the diamonds here. There's 13 of them. Then after you pick a diamond, again, you just picked one diamond out. There's 51 cards left in the deck, and 12 of them now left are diamonds. Let me do some of this stuff on calculator, because I don't want you to leave your answer like this. And you can see how I did this on my calculator. This is kind of nice. Oh, you can't see it anymore? This is 1 out of 221, and this one was, oh, it just disappeared. I thought I could do all that at once. 1 out of 17. Okay. All right. Jar contains 3 red, 5 green, 2 blue, 6 yellow. This is all in one jar now, and marble is chosen at random after replacing big piece of information. A second one is chosen. What's the probability of choosing green and then yellow? All right, let me make the tree diagram. Okay, so I got this far into the tree diagram. I don't know how many of you are laughing at me, and I realized this is a ridiculous way to do this. Let me try this again. We can still think of this as a tree diagram problem without actually drawing the whole tree diagram. The tree diagram on this is ginormous, but we can still think in that way. So, all right, so what's the probability of choosing a green? All right, so the green is 5 out of, oh, I didn't count these up yet. 5 out of 16, looks like. And then we put it back, so we're back to the jar of 16, and then what's the probability of yellow after that? The yellow after that is 6. So this is 30 out of 256, it looks like. Okay, that's not bad. I didn't have to make a tree diagram or nothing. All right. All right, whether or not you were the goalkeeper of a soccer match depends on who the coach is that day. Okay, so here's a hint that this is going to be dependent. I should have paused here. This was definitely independent events, right? Since we're replacing, this second draw out of the same jar has nothing to do with the first one. This does not affect how the second one's going to have its probabilities distributed and everything. But here we have a dependent situation. So if Sam is coach, probability of you being goalkeeper is 50%. But if Alex is the coach, I don't know, Alex doesn't like you as much or something. Maybe his kid is on the team. Probability of you being goalkeeper is only 30%. On average, Sam coaches 60% of the games, is what it says here. Now drawing a tree diagram is good because this is kind of a different situation. So you got to think about, okay, there's 2 different kind of parts of this story. There's who's the coach and then whether or not you get to be the goalkeeper. And you have to think about which thing comes first in this tree diagram situation. Like, should this branching stage represent coaching or goalkeeping? And should this branching stage represent coaching or goalkeeping? Well, you got to think about which one affects the other, or like which one is kind of in charge here and which one is affected by that. Well, it says here, with Coach Sam, probably of you coaching is this, or probably goalkeeper is this, and with this coach, the probability is this. So the goalkeeper is the thing that changes. The goalkeeper is the thing we have to have 2 separate probability stories about, right? There's a goalkeeper where it's 50-50, and there's another goalkeeper situation where it's 30-70. So I know the goalkeeper stuff is going to go in the second part. This is going to be like, are you goalkeeper? Yes, no. And that is dependent upon if it's Sam. Whoops, I guess I should write this over here. That's going to depend on if it's Sam is the coach or Alex is the coach. And this is 60% of the time, and this is 40% of the time. Okay, then I can finish that. Okay, and again, the whole this whole thing adds up to 100%, so life is good. And then again, once I got all of that, these questions are no problem. What's the likelihood that today is Coach Alex, and you are not goalkeeper? So this is the Alex and no. This is 28%. You can just write it right there. Okay. What's probably you are goalkeeper today? Well, that would be all of those plus all of those. This is 42%. There's a 42% chance you are goalkeeper. Some of that's with Alex, and some of that's with Sam. All right, we're finally on lesson 3. Think about these letters as if they're like Scrabble tiles. They're all different, which is helpful. Later, there's going to be some of these where some of them are the same. How many different 5-letter arrangements can be made? Okay, 5-letter arrangements. That would mean C-O-U-R-T would be different than C-O-U-T-R or O-C-U-R-T. Like, they'd be different if they're in different orders. So that makes a huge difference. We're going to talk about that a lot today. How many 5-letter arrangements can be made using these letters if no letter can be repeated? No, they're not asking probability here. They're just asking you to count. How many different ways can you choose 5 of these and make like a 5-lettered scrambled up word? Well, not really scrambled up word, but a kind of a listing of 5 letters and a code kind of thing. If no letter can be repeated. Oh, so if we had to use these as Scrabble ties, we couldn't repeat them. How many are there here? 9. There's 9 choices for the first one. This is kind of like some of the stuff we did earlier today. There's 8 choices for the second one because it's like picking a card out of the deck. I've only got 8 choices left, etc. So there's just going to be this many. Let me figure that out. Believe it or not, that's over 15,000. Yeah, that's a lot of ways to do that. It's like combination locks are so secure. Okay. All letters are vowels and no letter can be repeated. Okay, so we can choose from O, that's an O, U, E, A, oh gosh, what about Y? I think, yeah, I think in Canada, don't they say Y is always a vowel? Anyway, in here it looks like it's a vowel. If that's a word, I think it's a vowel. All right, all letters are vowel. I will make that clear on my assessments. I'll probably won't put Y in there because that's something to fight about. I hate fighting about that kind of stuff. And no letter can be repeated. We have 5 choices, so there's 5 choices for the first one, etc. This one you might be able to do in your head. I think this is 120. Pretty sure it's 120. Okay. Yeah, so this kind of repeated multiplication of descending numbers and stuff, that's a very common thing to do in probability. All right, if a random 5-letter arrangement is selected from the arrangements without repeats, and again, this is like independent events, right? Without repeats, putting the marble back in the bag kind of stuff. What's the probability? Okay, that it starts with a consonant and ends with a vowel. All right, so I think we're talking about out of this denominator. So all the choices without repeats, so this is why we're counting, because we need to count up how many go in the numerators and denominators. What are the probability it starts with a consonant and ends with a vowel? Okay, starting with a consonant, how many choices do we have? I believe we have 4. We're going to define Y to be a vowel. Then after we pick that consonant, how many choices do we have for the second line? You know what? We should probably choose I like putting these blanks in here. There's 5 blanks total, right? But the last one has to be a vowel. So let's put that vowel there next. 1, 2, 3, 4, 5, we said. There's 5 vowels. After I pick those 2 things, there's 2 letters gone from this. One's a consonant, one's a vowel. That doesn't really kind of matter, but 2 are, because now I can choose either a consonant or a vowel. Of the 9 that I started with, there's now 7 left once I've decided which one goes here and which one goes here. 7 for that one, 6 for that one, and 5 for that one. Let me figure out this fraction. Okay, so that turns out to be 4,200 ways out of those 15,000 or so, and it turns out to be a nice fraction, 5 out of 18. These reduce a lot, actually, so don't be surprised if that happens. Okay, two-way frequency tables. This is another way to organize data into counts. It's not very uncommon. I'm sure you've seen it before. Rows and columns tell you how these different kind of categories intersect. So, prom committee conducts a survey of 160 people. So this is nice. They give you the totals on the outsides here. They don't have to give you the totals, but they do here. If they don't give you the totals, you might want to draw them in. So they've made these columns here for it. It's kind of nice. So fill this out. Well, if this is 44 here and this one is, this has to add up to 69. That's not hard to figure out. This is 25. If this is 25 and this is 59, we just add sideways. That's 84. If that's 84 and this is 160, I believe this is 76, making this 20. I'm adding this way. 44 and 32 is 76. 32 and 59 is 91, and hopefully that adds up correctly. Okay. Find the probability of a randomly selected student from the sample. So from the sample, they mean out of 160. Again, I would continue to think, let's talk about denominators first. So out of the 160, how many are seniors? Because they'll change this. Randomly selected student from the sample, that's 160. If they said something like randomly selected junior, then that means this is not going to be 160. Anyway, randomly selected student is a senior. Out of the 160, how many are seniors? 76. Again, a lot of setup. Arms us with all the information we need for the answers. Out of everybody, how many of those people are juniors who are not attending? Juniors not attending is 59. That's a nice little intersection. Not attending in general, out of the 160, not attending in general is 91. Okay, I gotta make a 4th chapter of this video. Oh my gosh, I haven't done it in a long time. We're almost done. If a student was randomly selected from the seniors, okay, from the seniors is 76. That changes the denominator. What's the likelihood that she is attending the prom? That's 44. But that's a different question than what's the probability a random student is attending the prom. This is what's probably a random senior is attending the prom. That changes the denominator. All right, gambling and smoking. Well, this is an interesting context. Okay. They didn't put the totals here, so I would put the totals on here first. Let's do that. I think that's going to be a time saver because I think that's going to be most of our denominators. A person in the group selected at random. Okay, well yeah, I did need to know that because that's my 389. Out of these 389 people, how many of them gamble? It looks like 249. Yeah, I don't know where they get this context. I didn't make this up. All right, neither gambles nor smokes. Does not gamble, does not smoke is, again, we're talking about out of everyone, 389. Anyway, that group is the 58. And smokes or gambles. Okay, we haven't technically talked about how to do or yet, but let's look. Smokes would be all of these people, or gambles would be all of these. Let me get the highlighter out. Smokes is all of these, gambles is all of those. We only want to count the people who are in green, but we don't want to count them twice. So if I add up those 3 numbers, 152 plus 82 plus 97, I get 331. Okay, I promise the last one's going to be short. Okay,